Yeah, first of all, hello everybody. It's really a pleasure to be here. And today what I'm gonna present to you is the research I've been doing for my master thesis. I actually did my master in Italy, where I studied biology, but I did my master thesis at the University of Bristol, where I had the great opportunity to study the evolutionary history of sea spiders. So just to give you an idea of what a sea spider is, because they are kind of unknown creatures. So the common name, as I said, is sea spiders, and they are pycnogonids, and they are marine chelicerates that lives in the water of all the oceans. They can be found from cold water, warm water, abyssal, and littoral waters as well. So many people think that they are not really common and they are like few species, but actually I was also surprised to discover that currently there are 1,400 species described, and many of them probably not described yet because some species are small, they are mimetic, it's hard to spot them. And all the described species belong to 11 family of a single order, that is the order Pantopoda. So this is how a sea spider look like. So their body is divided into 3 segments, and the trunk, that is the central part that you can see here, is really reduced. And this led to an extension. Like, so where do we find the internal organs? We actually find them in the legs. So we have an digestive tract and the gonads that are extended into the legs. The legs can vary in number from 8 to 12. And we also have some structures like the proboscis that you can see here, and the oviducts that are unique in the animal kingdom, because like this is a kind of structure used to feed on prey. And the oviducts are cephalic appendages that are used by the males to bring the offsprings. So talking about their phylogenetic position, you can see that pycnogonids are the sister group of the euchelicerates. So investigate and understanding the evolutionary history of pycnogonids is really important to understand the evolutionary history of the total group arthropods. As I was saying before, currently we have just one living order, that is this one, Pantopoda, while the other 3 that are described are extinct and are all Tylozoic orders. While we don't have, interestingly, we don't have any fossil of pantopods before the Jurassic. So what did we do to investigate the evolutionary history of sea spiders? So first of all, we had to assemble a supermatrix to run our analysis, and we got our data set. So the data we were working on were not freshly published by us. It was downloaded from public repositories, and it comes from previous phylogenies. And we decided to work with 13 mitochondrial coding genes, the 18S, and 98 ultra conserved elements. So this was a kind of way for us to avoid biases in the evolutionary rate, because we decided to pick up genes that evolve at different rates. And we got these sequences for around 200 taxa of all the 11 families of pantopods that are currently described. We also include in our analysis 20 outgroups. And finally, we got an alignment after trimming that was more or less 22,000 base pair. So about the phylogenetic analysis, I will not spend too much time talking about this because this was not the objective of this project. It was just a step to get to the time estimation, but we used MCMCtree for this and Model Finder to pick up the best substitution model. And then we got to the point and to the divergent time estimation. To do that, we used the PAML package, like the MCMCtree from the PAML package. And we tried to test different models to see how the results varies. And we decided to test GBM and ILN clock models. And for that, we run 5 independent chains. Sorry. And here you can find some other technical information if you are into this field. And to calibrate our tree, we decided to use 5 fossils but we were not really sure about the taxonomic position of one of them. So we tested whether the inclusion of this or the exclusion of this was changing the results. Talking about the results, as I was saying, I will not spend time talking about the topology. I can just tell you that the topology is current with previous phylogenies. But about the fossils, here just to give you an idea of how we use them, here you can see the name of the node that has been calibrated, the fossil species, the range of time of which these fossils are from, and the reference, because for sure the fossils have been chosen with a criteria that were according to recent fossil reviews. And we decided to use the fossils as a calibration, using them as a hard, hard minimums and soft maximum constraints. Here you can see the ones that we decided to include. So Icaris from the early Cambrian that had been used to calibrate arthropods crown group. And then with Angocaris, always from Cambrian. And then we have a huge gap, and we go directly to the Jurassic, where we have Calostopantopodus, Paleoendeis, and Euryside that are all from the Jurassic and are all calibration points for pantopods, for families of pantopods. So we have this big hiatus, not because we were too picky in selecting the fossils, but also because, as you will see later, we have a really big gap in terms of fossil record for sea spiders. So this actually is a fossil that we didn't include as a calibration, but I think it is worth to spend a couple of words about it. So this was considered the first pantopod appearing on Earth. Actually, it was included as a calibration point for pantopods in the previous divergent time estimation. But the last year, some researchers described new material of this species, and they were observing some characters like the abdomen. And actually, it looks like it's segmented. And there are also some other characters in the anatomy of this species that suggest that this is not a pantopod. So we couldn't use it as a calibration point. So we had to exclude it and focus more on calibrations of the family's branches of our tree. So this is the time tree that we got in the end. And here you can see the calibration at their place with the red spots of where they are located in the tree. And from this, we can say many things. But the key points of this is that if you want to know how old are pycnogonids, we can have a look here. And we can say that they originated in the Cambrian in an interval spanning like 540, 510 million years ago. And at least 75 million years later, pantopods appeared on Earth. So you can have a look here. And then we had, after that, a diversification of all the families that are currently living So with these results in our hands, what can we say? We can say many things, but first of all, we want to have a look at the focus of this research, that was to try to understand what happened in their evolutionary history in terms of total group, in terms of families, in terms of relationship in between the age of the families. And we can see that the origin of pycnogonids total group is more or less 100 million years before the one of the order of pantopods, but at least we can say 75 million years. And that the first fossil of pantopods appeared more or less 200 million years after the estimation we have for pantopods' age. And considering this, we were like wondering why there are no more ancient fossils of pantopods. And here, just to visualize better the situation of the fossil records, here you can see all the described fossils of pycnogonids. There's a big gap here in between the Paleozoic fossils and the Mesozoic ones, where many extinction events occurred. And everything that is on the left is non-pantopod. Everything that is on the right is pantopod, according to recent fossil reviews. So according to our results, the age of pantopods is like the origin of pantopods should be here. So like more or less like here. So why there are not pantopods in the Unzruk fauna? the answer could be really simple. Like I can say probably they were not in that place at that moment, or it could be related to their ecology, to their sites, to their potential, their fossilization potential. But it still remains a mystery. The great thing would be to have some fossil from this period of time, but currently there's nothing, for what I know, or what we know, from this period of time. So we can also say that our results should be kind of representative of the evolutionary history of Pantopod's total group, because we cover the 13% of the total Pantopod known diversity in terms of number of species included in this work. We can say that Ascorhynchid was the first family of Pantopods appearing on Earth, and that our result is coherent with previous molecular estimates, except for some intervals that are, like, most of the intervals in our case are smaller, so they are more precise, and they tend to be a bit younger. The main difference is related to the age of Pantopods. So we estimate that they are around 60 million years younger compared to the previous study. And also our study is in contrast with divergence, in contrast with timescale that are based just on fossil records. Also the previous molecular study, but this is probably related to the sporadic fossil record that we have, to the poor conservation of most of the fossils, and for this big gap of years in which we don't know what pycnogonids were doing on Earth. So just to conclude and to give some dates, we can say that pycnogonids probably appeared during the Cambrian. Pantopods appear at least 75 million years later, and the families of Pantopods diverge shortly after this. What can we do to improve the knowledge we have for this topic? Yeah, it's easy to say discover new fossil specimens, but this would be really great. This would be really interesting to see, like, the kind of sea spiders that you can find around in that period of time. And something that we can actually do right now could be to combine phylogenetic analysis of molecular and morphology by including also the fossils that we have. So by including in the morphological matrices the fossils of the spiders that are described. And something also that would be really useful is to do consistent sampling of extant spiders, because there are some families that are really poorly sampled, for which there are just few sequences, and that they are not even of a good quality. So this could be really useful. So I would like to thank all these people that contributes to this research, and in particular Sandra, that was my mentor from the beginning till the end, and a really great inspiration, and all the people, the amazing people from the Paleo Lab in Bristol. And thank you also for listening to me. I would be happy to answer any question, or just if you get some question after a while, this is here on the side, you can see my contacts, and I will be happy to be in touch. Thank you.